Okay, I've gotten a few requests for this, so I'm just going to quickly do a video over intermolecular forces and specifically how those impact boiling point and solubility. So intermolecular forces are the ones that we're going to talk about in organic chemistry. There's three main ones, and that is dispersion forces, dipole-dipole, and hydrogen bonding. And I really hate the name hydrogen bonding because that makes it sound like it's a bond, but it's not really a bond. So sometimes I call these, this is what I call them, this is what other people call them, so don't use this for other people, but sometimes I call these super dipole because they're just really strong dipoles. So we'll talk about what that means. I actually think it's easier to start with dipole-dipole. So for dipole-dipole, if you have a hydrogen bonded to something that, or any bond, I guess, any atom. So we'll say we have atom 1 and atom 2. And if these atoms have the same electronegativity, the two electrons will be shared equally between them. So like if we had a fully covalent bond and we have two of the same atoms, two of atom 1, the electrons would be equally shared between them. But often one atom is more electronegative. So let's say that atom 2 is more electronegative. I'm just going to write E neg. It's more electronegative. And so it is better able to draw these electrons towards itself. So instead of these two bonds being equally shared, or the electrons being equally shared, it's more like the electrons are shifting over to be closer to atom 2. So there is one side that has extra electrons than the other. So we would say that that side is a little negative, and the other side is a little positive. So if we're looking at these, one being a little negative, one being a little positive, if there are, if there's another molecule that's like this, that has this same dispersion of atom 1 and atom 2, the partial positive on this side and the partial negative on this side will be drawn to one another. So intermolecular forces are this force of attraction between two molecules. So the between two molecules, that's where I'm getting at intermolecular, so between two molecules. And then forces is the force of attraction. So the strong dipole present here pulls the electrons towards one side, leaves the other side as positive. So this arrow that I drew right here, this is called a dipole moment. You can see that it's pointing in the direction the electrons are being pulled, and then we cross the other side to say like, oh, this side's going to be positive. This side will be more negative. But if we have this strong dipole moment on one side of the other, there's attraction that comes between these two molecules that will make them stay closer together, okay? And why does that matter? Well, if you think of solids, liquids, and gases. Oh, I forgot that I was on the laser pointer. Solids are a bunch of molecules that are really close together, and they're held together in this solid state by their intermolecular forces. So the forces between these two, I'll draw this with a dotted line. I think that'll be easier to see. The forces between these two that are attracting one another, between these molecules that is attracting one another, these are the forces that are keeping them together. So intermolecular forces are holding these things tight, close together in their solid state. Now if we think of something being a liquid, these atoms are still relatively close together, close enough that they're sort of making a unit, you know, it's like you have a body of water, or a body of, you know, like a a glass of alcohol or something. So they're still attracted to one another, but they're not so attracted to one another that they are stuck close together. And that's because we put in heat between part 1 to part 2. Oh, I didn't want this to still be a dotted line. From part 1 to part 2, we put in heat. And that heat basically started to give these molecules enough energy that they can move around a little bit more and they can overcome those intermolecular forces. And then if we continue on and we put more heat in, these are going to go further and further apart. The atoms are going to have enough energy to where they don't need to be near each other, and they're going to be really far apart. And there are basically no intermolecular forces. So this is what air is this is just empty space between molecules. So that is the gaseous phase. These gaseous phase is when these molecules are not interacting with each other at all. So when I say that intermolecular forces impact boiling point, this is what I'm referring to, is this like idea that stronger intermolecular forces, if they're able to hold things together, they'll stay a solid. And then as we add heat, the intermolecular forces start to be overcome. They become a liquid. And then if we add more heat, there are no intermolecular forces, no dotted lines here at all. And this last one, we don't have any dotted lines here because there's no intermolecular forces there. And how easy or hard it is, how much energy you have to put in, depends on how strong are the intermolecular forces. So the amount of energy depends on the intermolecular forces. So stronger intermolecular forces are going to mean that we have a higher boiling point and a higher melting point. So let's go back to the intermolecular forces we were talking about at the beginning. I showed you like basically what they are. And I use dipole-dipole, where if we have any polar bond, this is what happens. Now, hydrogen bonding is like a super dipole-dipole because hydrogen is bonded to oxygen, fluorine, or nitrogen. And these are some of the most electronegative atoms on the periodic table. And so there's a really strong dipole here. And so it's so strong that it kind of starts to become fuzzy if we have a really strong dipole, and then we have another water molecule with a really strong dipole. This water is so negative on one side and so positive on the other. This little delta means partial, by the way, partial positive. It's so negative on one side and so positive on the other that it's gonna, one positive side is going to be really strongly attracted to the negative side of another atom, of the other water molecule. And it starts to become unclear, really, is this hydrogen still bonded to this oxygen? Or is it starting to be bonded to that oxygen? And so the attractive forces, that intermolecular force between two molecules that have a hydrogen bonded to a really electronegative atom, starts to almost act like a bond. And that's why we call it hydrogen bonding. But it isn't a true bond. It's just like a really intense dipole. So it's the same effect as a dipole, but only if hydrogen is in a very strong electronegative pull. And so that only happens with hydrogen bonded to oxygen, fluorine, or nitrogen. So my high school teacher said it was H with fun. And I remember being like, well, it isn't fun F-U-N, but you know what? Looks like not, because I still remembered it. So H with fun, H with F-O-N-N. That's when you get that super dipole. But if it's like H with chlorine, that's just considered a regular dipole. So, and then the weakest intermolecular forces are, I think, the hardest ones to explain. So if you have two molecules that are exactly the same and they're perfectly evenly sharing their covalent bonds, and so there's not a permanent dipole. So a good example of this is like if you had two hydrogens bonded to each other or two nitrogens bonded to each other. These things are going to be perfectly equally sharing their electrons. But if they come near another atom, so let's say another hydrogen atom comes here, these electrons will start to repel the electrons from the first hydrogen atom will start to repel these other ones. And so very temporarily, we have, I'm going to draw this up, instead of the electrons, say these are all electrons, are all negatively charged, evenly shared between two atoms like this, as they come closer together, the electrons from one side are going to start to repel the electrons from the other side because they're both in negative, and so they're going to be repelling one another. And that'll leave an absence of electrons where the absent electrons are gone, and just temporarily these will be attracted to each other just while they're near each other. And I often call this the bridesmaid effect. If you've ever been in a wedding, you know that just for the time being, just transient for the time of the wedding, the bridesmaid party gets together and they have an induced bond, an induced intermolecular force around the bride. So they throw the shower, they throw the bachelorette party, they have the wedding, and then after that, it's like they go on and there's no attraction. There's no bonds that are still present. It's like we were only together as a crew because we were supporting the bride. So there's like a temporary bond and then we all go away. And that's very similar to what happens with dispersion forces, where as they come near each other, they have this temporary induced dipole from one another, and that temporary thing bonds them together, but once they're not near each other anymore, there's no attraction that's keeping them together. So if two nitrogen atoms were just floating around in the air, they wouldn't interact with each other at all, and there would be no dipole. But if they happen to come close to each other, just temporarily, one side would become negative, the other would become positive. They would be attracted to each other just for the moment, and then they would keep on going once they separated back out, once they got enough energy to move on. So, and those dispersion forces are present in everything. Dipole-dipole is only present if you have a very polar bond. And the bond and the molecule, it's if you have a very polar molecule. And if you're not sure about the difference between a polar bond and a polar molecule, I have another video on that. And then for hydrogen bonding, this is only if you have a hydrogen with fluorine, oxygen, or nitrogen. So I hope that was helpful. Let me know if you have any questions, and I'll do my best to answer them. Good luck, stay.